is Tim Wigger. I'm working for Professor Tom in Portsmouth, and at the moment we're working on near-tip strain fields and welded steels, which we map using PRC and EDX. We had to alter the title a bit because we included more of recent results. But, generally, as we all rely on electricity, and mostly electricity is generated by heat engines, we depend on power plant turbine rotors, which can be produced by forging or are nowadays usually produced by welding, which has advantages. We have a shorter lead time for replacement of these parts and lower production costs, and we can also make them hollow, which makes them lighter. On the other hand, there are issues with welds generally, as welds are quite complex due to material property mismatch. Different materials are combined, and due to microstructural changes that occur during welding due to heat effect. So we saw the need for a structural integrity assessment to deal with potential defects of welds. Welds can fail due to fatigue, that's what we are interested in. Also due to creep, stress, corrosion, cracking, or other mechanisms. Currently, approaches to structural integrity of weld structures are mostly empirically or based on semi-empirical studies, and complexity, the actual physical mechanisms are not very well understood. That was a challenge for us to do a fracture mechanical assessment of fatigue cracks in the heat affected zone next to the weld. So we wanted to look at the influences of the change of microstructure in the heat affected zone, and what the influence of the variation of the material properties is, and to do a quantitative, or to find a quantitative life assessment strategy for long-term safe operation, because we all want our electricity to be cheap and reliable. More specifically, usually for crack growth, linear elastic fracture mechanics are used with the stress intensity approach, which does not include the plastic deformation that occurs right in front of the crack tip under small-scale healing conditions. And according to numerical simulations and former in-situ measurements we did in our group, this failure right in front of the crack tip within a few microns is probably due to strains accumulating progressively, so due to a ratcheting phenomenon. And as soon as the accumulated strains reach a critical strain, the material fails and the crack grows a tiny bit. We define as our aims for now to study the evolution of these near-tip crack strains normal to the crack plane, and we captured them near a stationary and near a growing crack in the heat affected zone using digital image correlation to the surface strains and energy dispersed X-ray diffraction for the pulp. And we do these experiments on specimens of welded rotor steel. This is a combination of two materials basically. The base material is a 30 chrome nickel steel. The heat affected zone consists of martensites and bayonites due to the heat influence while welding, and we have a grain size of 7 to 50 microns near the crack tip. When we measure, it's around 7 microns. The welded metal has a slightly lower carbon content, nickel and manganese. Here's an overview. Worth mentioning is probably the quite high yield strength of around 800 megapascals. To study this, we made specimens, compact tension specimens, with the base metal on top, the welded metal at the bottom, and the crack and the crack tip are located in the heat affected zone. Here's a micrograph. The cracks did grow, so this is the pre-crack. They did grow at a certain small angle, but we considered them to be straight to keep things simple. The length is around 3 millimeters. We mounted the specimen on a usual servo hydraulic testing rig for the DGAC experiments. We applied constant fatigue load, constant amplitude with a low load ratio and load control. And in situ, we recorded images of the surface during the fatiguing. Before that, we had to etch the specimen surface to generate enough features on the surface to be able to correlate. The resolution of these images is about half a micron per pixel, which is quite close to the optical limit. And this whole analysis was done with Davis software, commercial software by Vision, which allowed us to generate strain and displacement maps like this, and we were mainly interested in the area right around the crack tip. First of all, we measured normal strains near the stationary crack. We applied quite low loads. The crack has probably grown a bit, but we considered it as stationary because it didn't grow more than a pixel. In front of the crack tip, we measured the strains in square-shaped areas of interest. To do that, we recorded during fatiguing, every time at maximum load, we recorded an image and correlated it to an image at minimum load. The size of these areas of interest is similar to the 7 micron size of the grains. So we use 6.5 microns. And we have 8 positions which slightly overlap. Now, if we plot our strains versus cycles, we can see all these different colors are different positions, 1 to 8. We can see in this example that the strains increase slowly with the cycle. So we have some sort of accumulation or ratcheting. This was done on 2 different specimens and at 3 different loads. We can see an increase in every case. You can also see that on different specimens we have strains on a similar order of magnitude, but the increase rate varies. So depending on if the crack grows on the surface in this moment or maybe in the bulk, we get a different increase. However, an increased ratcheting is evident. Of course, we also wanted to know how this behavior is on growing crack. So we did 2 experiments. We grew the crack first on a slightly lower stress intensity by about 1 millimeter, and the second experiment at slightly higher stress intensity by another millimeter. And during that, we recorded images again and tracked the strains at select positions along the crack tip. So what we obtain is each line is one tracking position, and the strain is quite constant until the crack tip approaches this position and it goes up. So this increase is again a sign for accumulation, actually. These marks here show the point at which the crack tip is exactly at the position of the measurement point. And these points are scattered around a certain value, which is the critical strain, which we assume is the strain necessary for the crack to grow, or for the material to grow. This critical strain seems to depend on the stress intensity. It seems to be, it's higher at the higher stress intensity, and you can see we've reported this with a rather small area of interest and repeated it with a larger one. You can see here, we can see the same phenomenon, just at a lot lower strain here. So that means if we use a smaller area of interest, which is closer to the crack itself, we record unsurprisingly higher strains as when we use a larger one, which includes more of the surroundings and more averaging. Why did we do that? To be able to compare it with the second method, the EDXD measurement. We did place a diamond, B1 so that's based on atomic lattice deformation to acquire bulk elastic strains. We also applied a constant amplitude fatigue load, and the gauge size of the X-ray beam was about 100 by 100. And the gauge size in the Z direction, so in the specimen itself, is about 4.5 millimeters, where the diffraction occurs. What we obtain is strain maps like this. The crack part is approximately indicated here. And we did similar measurements as the first on the stationary crack. We tracked several points around the crack tip while applying the relatively low load, and it seems the values are kind of constant, so we can't see any ratcheting behavior, simply because this gauge volume or this gauge area is too large or too insensitive to measure strains which are right in few microns in front of the crack tip. But we also repeated this on growing crack. Similar to before, we tracked several positions in the crack pan. The crack grew approximately around here. Over 2,000 cycles at maximum load again. And what we can see, we have an accumulation strain at all these positions, and marked here are again the points where the crack tip hits the tracking point, and these points are again at a constant or at a similar level. So the critical strain this case would be around 0.6. Simultaneously, we recorded DIC images on the same specimen in the same situation, and we also have more scatter but a constant load. Now, the DIC is a bit higher because we have plastic strains and elastic strains in there, and it's a surface measurement, while the EDXD only captures elastic strains and in the bulk material, and the strain gauge is larger in Z, which causes more averaging. To sum this up, we examined the fatigue crack behavior in the heat affected zone of welded power plant rotor steel with DIC and EDXC. We can see that strain ratcheting occurs on the surface and in the bulk. On the surface within 1 to 2 grain sizes, maybe even more, but it gets less significant if we go farther away from the crack. The critical strains for crack growth appear to be under similar conditions, with loading and experimental conditions, regardless of their position. Also, they seem to be proportional to the applied stress intensity factor, approximately. Lastly, the bulk elastic strain measured by EDXD is lower, as I explained before, and I think this confirms the models our group has set up before, which predicted the similar behavior to this. However, this work is limited. The EDXC method seems to be rather insensitive to low strains or low strain gradients. So to capture these stationary low gradients, we would have to use a smaller strain gauge. Also, the measured strains depend on the size of the area of interest, of course, depending on how much we average around the crack tip. And finally, we only used a limited number of specimens, which we measured under selected loading conditions. So before we generalize this, we would have to do some experiments.